You see, oh, okay. Can you see my cursor?
Yep.
Okay, nice. So, can I start?
Yep, go ahead.
Okay. Hi, everyone. Today I'll be talking about my latest paper together with my, which I wrote together with my thesis advisor, John Sterling, and it's about multi-clock synthetic guarded domain theory. If you don't know what SGDT is, I'll abbreviate a synthetic guarded domain theory. It's a mouthful with SGDT from now on. Well, if you don't know what that is, it's a domain theory for guarded recursion. And well, I'll explain in a second what guarded recursion is, but if you don't know what domain theory is, it's basically a theory of computation based on recursion. And well, another particularity of SGDT, and that's what makes it synthetic, it's that it takes place inside a topos. And the structure we require to call a topos a model of SGDT is, well, we should first of all have an endofunctor that's at the very least left exact, and we'll call this functor the later modality. And this functor, moreover, has to be pointed, so there is a natural transformation which we'll call next from the identity endofunctor to the later modality. And moreover, it's an applicative functor, so it's just short from being a monad. And well, it's actually important that this isn't a monad. And also it has to be a dependent functor. And by that, I mean that it induces a copy of itself on each of the slices of our topos. And it has some nice type theoretical properties, like being well behaved with respect to substitution and dependent products. And also, we're asking for some properties for some structure inside of our topos. Namely, we're asking for this guarded fixed point property, also known as lobe induction, which tells us that for each f that goes from later x to x, where x is an arbitrary object of our topos, there exists a single guarded fixed point. And what do I mean by guarded? Well, as you can see here, this looks like a fixed point, but it comes.
Are we supposed to still be seeing the first slide, or have you moved on?
I should have moved on.
Okay, you might need to.
Okay.
Oh, there we go. Okay, that's
them. Okay. So now you can see that. Okay, I'm sorry. So, okay, let me start over. So we have this endofunctor, which is left exact. We'll call that the later modality. It's a pointed endofunctor, so there's a natural transformation from the identity to the later modality. It's an applicative functor, and it's also a dependent functor. And by this, once again, I mean that it induces a copy of itself on each of the slices. Here you can see there are something indicating that this acts on slices too, and also it should have some nice properties, nice type theoretical properties with regards to substitutions and taking dependent products. And in the internal language, we're asking for this property. Okay, as you can see here, this is kind of a fixed point, but not really, because it comes guarded under the application of the next morphism for x. Okay, so it's almost a fixed point. It's a fixed point up to composition with next, and that what makes it guarded. And so the archetypal example of a model of SGDT is the topos of trees, or well, pre-sheaves over the pre-order of natural numbers. And just to give you an idea of what do objects in models of SGDT look like, well, an object in the topos of trees is a chain of approximations. So, well, a type in your underlying type theory of the topos of trees is approximated at several stages, and by going in the opposite direction of the restriction mappings of your pre-sheaf, you basically increase the accuracy. And the action of the later modality decreases the accuracy of your approximation by just, adding a singleton set on top of your chain of approximations. And the action of the next morphism just maps an approximation, a chain, to the chain with a singleton mapped on top of it. So it decreases the approximation of your chain. So among the many interesting uses of SGDT, we'll focus on one in particular. But first, let's recall what recursive types are. So recursive types, also known as free algebras, are fixed points for endofunctors that are both initial algebras and terminal coalgebras. And the main example for recursive type is, well, fixing an object A or a type A of our topos. We can build the free monoid on it, or the object of lists of elements of A. And yeah, this is the fixed point for the functor that sends X to the coproduct of the singleton and A times X. So this basically gives you the two constructors for the list type. So the singleton represents the empty list, and the product represents the list constructor. So because that's what you're doing the recursion on. And our running known example will be streams, which are basically infinite lists. So as you can see here, the endofunctor for streams just maps X to its product with A. And yeah, basically we don't have the base case for lists. So it's kind of like a list, but to build a stream, you can only take a pre-existing stream and attach a piece, a new piece on top of it. And yeah, these aren't free algebras, these aren't recursive types, but just a terminal coalgebra or a co-inductive type. And if you've ever programmed in Haskell or Idris or Agda and tried your hand on co-inductive types, well, you'll know, you probably know what a pain to program in this stuff is. So we'd like to approximate streams with a type that it's actually a recursive type. And we can do that by leveraging the fixed point property of synthetic guarded domain theory. So if we have a universe in our topos, we know by the fixed point property that for each endomorphism of the universe that satisfies this property, well, this yields a free algebra. So we have a way to construct to construct new kinds of recursive types, and we'll call these types guarded recursive types. So the main example is guarded streams, which are an approximation of streams. This is a recursive type, and let's look at the endofunctor that generates it. So it sends X to A times later X. So it's like streams, but in this case, the recursion comes under the guard of the later modality. So that's why it's guarded. And well, let's see how it looks like in the topos of trees in our example model of SGDT. Well, it's a chain of increasingly large products of A. So yeah, and the restriction mappings are just projections on the first n members of the product. So let's compare a bit the type of streams, the type of classical streams, and the type of guarded streams in the topos of trees. So as you can see, streams of A, it's just the constant per sheaf of the product of an infinite number of copies of A. And yeah, as I showed you in the last slide, that's the type of guarded streams on A. And let's compare a bit the pros and the cons. Okay, first of all, this is a reasonable approximation because after infinite steps, the approximation like converges to well, an infinite product of copies of A. So it's totally reasonable. And yeah, while the classical streams have no induction principle because they're not recursive types, and so it's, for example, hard to specify total functions. You'll have to rely on pretty arbitrary and brittle syntactic checks, like you'll have to always do recursion under the application of the stream constructor to be sure that this that the functions you're defining are actually total. Well, in the case of guarded streams, you're okay. You can just use the induction principle and you're sure that the function you're building is total, and you can build basically all whatever you want. Well, whatever the type discipline enforces. And let's see the cons of guarded streams. Well, while with classical streams, you can just project out whatever item, whatever member of the stream, whatever element at whatever place you like. So I want the nth element from the start of the stream. You just project it out. There are projections for each place in the stream. For guarded streams, you just have an approximation to projections. So if you want the nth element of a stream, well, of a guarded stream, well, you can't have that, but you can have a promise of the fact that after n steps of computation, you're gonna eventually have the element you wanted to project out. And for another example of things going wrong with guarded streams, here's a totally reasonable function one would like to program with streams, which basically takes a guarded stream of type A and takes the first n elements of it and gives you a list of these n elements. And this is a really simple and totally reasonable definition for this function, but it doesn't even type check for guarded streams because here the take function is doing recursion on AS on the rest of the stream, of the guarded stream, but this is not a guarded stream, and the take function is expecting it, but it's receiving a later guarded stream. So the promise that after a step of computation, I'm gonna have a guarded stream. So this clearly doesn't work even for the most basic things, but it's, well, the idea looked nice. It's nice to have recursive approximation of these co-inductive types, not only streams. You can do that for many other things. So is there a way out? Is there a way to keep the good things and then, well, get a reasonable way to program on streams? Well, yes. So Atke and McBride came up with this nice idea of parameterizing the later modality over a collection of what they call clocks. Basically, they're parameterizing this later modality over an object of your topos, your model of SGDT. And by these, you can now take dependent products over this object of clocks and eliminate the later modality. And with this, we can recover streams from guarded streams, because now we have this family indexed by K of later modalities. And so we have this family of guarded streams at index K. If we take the dependent product of that over the whole family, we get the classical type of streams. And well, that's nice, but they left some stuff out. So for example, they defined a programming language and a non-dependently typed one. And we were talking about a categorical semantics for a type theory, right? So there's clearly something missing, but luckily Bishak and Mogelberg and Sterling and Harper independently came up with solutions with models of multi-clock synthetic guarded domain theory in a pre-sheaf topoi. So we have dependent types and we have a categorical semantics. There were still some questions open, like they gave two very concrete models, and well, there were only two. They didn't give a family of models, and it wasn't clear how they were related to the single clock, the classical SGDT models, and how they were related with one each other, and also, well, it would be nice to have well, more of that, not just an ad hoc construction for a single model. And our contribution was to actually come up with a universal property that relates single clock models and multi-clock models of SGDT. And also we generalized constructively all the classical constructions and results from the original paper defining models of SGDT to a bounded topos theory over an elementary topos with a natural number object. And we also showed that models of SGDT are closed under taking internal per-sheaves and Lex localizations. So for this talk, I'm going to focus on this first portion of our results. And so let me introduce what an elementary topos, a bounded topos over an elementary topos is. So if we fix B an elementary topos with a natural number object, a bounded topos over B is a morphism of elementary topoi, okay, such that the gluing fibration has a small separator, and this is kind of equivalent to the classical Giraud axioms for Grothendieck topoi, but in a over something else setting. And let's see what a geometric theory over B is. Well, it's a family of source, a family of predicates, and a family of sequence in which these, these predicates, phi and psi, are defined using arbitrary unions indexed over objects of B. So this I is an object of B. Finite intersections, existential quantification, and equality, okay? And we know that for each theory over B, for each geometric theory over B, there is a bounded B topos that classifies it. And by that classifies it, I mean that taking a geometric morphism from a topos X to the topos that classifies the theory T is equivalent to give a model of the theory T inside the topos X, inside the domain of the geometric morphism. And also we know that each B topos, each bounded B topos classifies a theory over B. So, well, this covers pretty much all the B topoi and all the B geometric theories. And now we can define our main instrument for proving the stuff we proved, which is the lower bag topos construction. It's more complicated than that, but I'll just give you an idea of what it does on the theory classified by a topos. So if we have a theory T over B, the lower bag topos of its classifier is the bounded B topos that classifies the theory of T models, of models of T, that are indexed by an object K. And so let's make an example. If we take the topos of trees, so remember it's pre-sheaves over the pre-order of natural numbers, these, the topos of trees, classifies the theory of filters over the poset omega, so the poset of natural numbers, and a geometric morphism from X to the lower bag topos over the topos of trees is given by an object of X that indexes and a K-indexed filter on omega. So, well, this family of filters is indexed by this object. So this makes sense. This fits the description of lower bag topos. And our main results were that the Bijak and Mogelberg topos is actually the lower bag topos applied to the topos of trees. And our main result is that if we take E, a bounded B topos that carries the structure of a model of SGDT, then taking the lower bag topos over it gives you a bounded E topos, so we're changing base. That's a model of multi-clock SGDT. So it has this whole index family of later modalities. And yeah, with that, I'm done with the talk.
Thanks, Daniel. So thank you, speaker.